Okay, thank you, Gabriele. And it is for me a great pleasure to be here. And in these few minutes, I will try to describe some new work that has been carried on with Professor Valerio Lucarini from the University of Reading and Dr. Francesco Aragone from Université de Lyon, École Normale. And this is basically a natural continuation of some I would say decade-long work on the applications of the response theory to the climate system. And as I'm not a mathematician, I hope that you will forgive me for not being specific about some of the terminology, and I hope I will be able to answer all your questions. As Gabriele already said, I come from climate science, so I would like to start my discussion about the problem of modeling the climate system. So I guess that some of you already know what a global climate model is. Basically, it is a set of ordinary differential equations that are solved on a three-dimensional grid at every forecast or integration step. Processes that are not explicitly accounted for in the ODEs are included in terms of parameterizations, meaning that are solved in terms of the are solved diagnostically in terms of the effect that they have on the prognostic ordinary differential equations. From the point of view of climate system, it is important that this kind of climate models is defined in terms of its boundary conditions. Boundary conditions can mean different things in the context of climate system, but I would say that the most important thing when one wants to perform a climate prediction to models is defining the conditions that affect the radiative transfer in the system. So particularly, this means that the boundary conditions that are used in climate prediction are the evolution of the atmospheric composition, the land use change. And if we are talking about atmospheric models instead of coupled models, boundary conditions can also mean imposing the sea surface temperature at the lower boundary of the atmosphere. The Climate Model Intercomparison Project is a community effort to bring together simulations with climate models that has allowed to standardize the protocols of climate model simulations over the years, and defining a set of core experiments that are needed in order to understand, on one hand, the model performances, and on the other hand, gaining more insights on the evolution of the climate system, where the observations basically cannot arrive. And these experiments are named after DEC experiments and consist of unperturbed pre-industrial condition simulations where the boundary conditions are kept fixed at the stationary state, defining the atmospheric composition and the land use before the industrialization. An experiment with the abrupt quadrupling of CO2 concentration, where the CO2 concentration is instantaneously quadrupled at a specific time during the integration. The so-called 1% CO2 experiment, where the CO2 concentration is increased linearly by 1% every year until doubling. And then the historical simulation, where the model is allowed to evolve according to the evolution of the forcing condition through the 20th century. So from the, well, actually from 1870, from the conditions representative of 1870 to nowadays. Outside of this set of experiments, there is the set of future climate scenarios that are defined according to what are the what is the atmospheric composition that is predicted for the next century and beyond, according to socioeconomic models. Here I show an example of that, where the newly developed SSP scenarios for the CMIP6, for the sixth phase of the CMI project, are compared with the RCP scenarios that are representative of the CMIP5, phase 5 of the CMIP experiment. So every time we move forward in the definition of the phases of the CMIP projects, there is a massive increase in the amount of computational resources that are needed for carrying on the simulations. As you can see in this table from Umenhofer 2019, the amount of data storage required for CMIP5 is 50% the amount that was needed for CMIP3, the previous phase. And for CMIP6, there is again an increase of a factor of 20 to 50. And this is something that is challenging the resources and the capability of the computational centers more and more through the years, especially because it is becoming more and more important and more relevant, the issue of providing not only a single model realization, but approach the problem in a probability, in a probabilistic way, providing for each simulation an ensemble of realization in order to sample internal variability, but also, as we will see later, to provide a consistent estimation of the force response, as we know that the response, the evolution of the system lies under certain condition on a pullback attractor. So as of now, we have a plethora of experiments with no clear strategy, at least from a scientific point of view, on how to carry on the or how to arrange the set of simulations that are actually needed. And the question is, can we do better? In order to answer this question, one has to take into account that first, a few basic issues. First of all, the force response should be tested against the internal variability, meaning that we need to take into account the impact of forcing on the internal variability of the system. Then the study of the force response has to be accompanied by theoretical consideration on the nature of the climate system attractor that might constrain the reasonable evolution of the system, of the model system. We have to take into account that not every model has the same skill. Not every model has to be weighted the same as the others. And for this, there are several smart ways to study the multimodal evolution of the force response according to the performance of the models. And many performance metrics have been developed in order to account for that. So in the end, what we will discuss about in the rest of this talk is what are the forcing scenarios that are actually needed to understand the force response of the system, and if we can use information from actual simulation to predict the response of the system to a desired forcing, without the need of carrying on the simulations with that specific forcing. So ideally, this would be the algorithm that we would like to have. we study the statistics of the free fluctuations of the unperturbed system. We use some transfer function or more generally the semi-group generated by the Ruelle operators to study the force response of the perturbed system, knowing the statistics of the unperturbed systems. There are several strategies to do that. One is for sure the fluctuation dissipation theorem that assumes that the force response projects on all the modes of the natural variability or internal variability, but these has some limitations because first of all, the force fluctuations might not be present in the statistics of the unperturbed systems, and this would mean that the FDT wouldn't allow to recognize or to predict what sometimes are defined as climate surprises or climate transitions that are not in the statistics of the unperturbed system, as I said. Another problem is that the climate system is actually not an equilibrium system, is a non-equilibrium system actually that adjusts continuously toward the statistically steady state. This means that we need to provide a generalization of the FDT, and we find this generalization in the response theory, and particularly in the definition of and description of the response theory that has been provided by Ruelle in the context of dynamical systems, basically assuming that, well, demonstrating that the evolution of the system can be understood in terms of the perturbation to the invariant measures that describes the unperturbed systems. So again, since I am a climate scientist and not a mathematician, I'd like to start addressing the problem from a very heuristic points of view. And this brings me back to the so-called cold start problem that was accounted for by Hasselmann in 1993. So this relates pretty much to the prehistory or history or far history, let's say, of the coupled climate model simulation. By the time in 1993, people were starting to couple the atmospheric models with the oceanic models, and started to produce climate prediction under anthropogenic climate change forcing scenarios. What people realized by the time was that it was desirable not to let the model run throughout all the evolution of the 20th century when the CO2 concentration were building up in the atmosphere, but it was desirable to define an initial condition that was representative of current days, and then let the model evolve according to the CO2 concentration of current days. And they realized that if they would compare this simulation with the actual simulation throughout all the 20th century when the CO2 concentration at the time to build up in the atmosphere, the simulation with current days conditions were systematically underestimating the temperature anomalies. In order to understand why this was happening, Hasselmann introduced a step forcing experiment in which the CO2 concentration was instantaneously doubled, and looked at the evolution of the system, and especially of the near surface temperature that are the basic proxy of climate change, as we all know. This problem can be easily assessed with something that is commonly used in signal processing, for instance, that is the impulse response approach. And I noticed that if we define a relation between the observable, that is in this case the near surface temperature, and the forcing, that is the CO2 concentration, as a simple linear feedback equation, as it is usually done for the definition of climate sensitivity. For instance, we can think about the Gregory model in these terms. The transient linear response of the observable could be written as the convolution of the time evolution of the forcing by the response function R, and the time derivative of the response function would be then the well-known Green's function. If we use the linear feedback equation in this context, we can see that the response function is can be seen in this way as basically an exponential relaxation process, for which, and of course, if we derive this response function in time, we see that basically the Green's function has the shape of an exponential decay. The interesting thing, even though I won't go further into that because I will be focusing on other things, is that actually for any generic non-degenerate linear system, the response function can be represented as a linear combination of so-called normal modes. So basically exponential relaxation with different time scales, with complex eigenvalues mu as lambda minus I omega. And this means that the Green function would be a linear combination of the of exponential decays at different time steps. And more recently, Lucarini and others have found that actually for any kind of evolution, the linear response can be seen as an infinite combination of exponential decays. So anyway, the Hasselmann's approach has actually a very rigorous counterpart, as I've already mentioned, in the response theory, the way it was defined by Ruelle in the late 90s. So if we consider a generic dynamical system as x dot equal to fx, where f is the set of ordinary differential equations that define our model, but we could say that define the evolution of the system. We assume that this system is smooth, meaning that it satisfies the chaotic hypothesis. What means chaotic hypothesis? For what is our concern here, it means that this high-dimensional chaotic system behave as an axiom A system, meaning that their ensemble and temporal evolution are asymptotically equivalent, and that the statistical properties of the are stable across the weak when a weak forcing is applied. If these conditions apply, so if we can apply the chaotic hypothesis, then we can perturb the dynamics of the system through perturbation of the form psi, where x. Sorry, can you see my pointer because I cannot see it, so it's a bit difficult to go through the slides like this.
I cannot see your pointer. Valerio. No.
Okay, so anyway, if we define the perturbation like this as x time f, sorry, where x is the spatial pattern of the perturbation and f is its time modulation, then the evolution of an observable phi in our dynamical system can be written as a series of perturbations around an expectation value of the unperturbed system phi 0, like in equation 6. So n represents the n-ordered perturbation, And the first order contribution reads as simple as the convolution of the green function by the time modulation of the desired forcing. And this is what we will be focusing in the rest of my talk. We want to see what we can actually describe with only the first order perturbation if we know the linear green function. So the green function is causal, so it is 0 for t less than 0. And if we reduce ourselves to the impulse response problem, so if we impose that time modulation of our forcing is some constant times an Heaviside function, then basically we go back to the Hasselmann problem. The difference is that actually we are not making any assumption about the relation between the observable and the forcing. So we are not assuming anything that looks like the linear feedback equation. The only assumption that we made here is that we are under the chaotic hypothesis, and that the forcing that we apply is actually a weak perturbation. So, remembering our tentative algorithm that I was showing before, now we can define it a little bit better. The first step would be posing ourselves in a comfortable situation of a step-like forcing, as in the case of Hasselmann. We can use an ensemble of realization to get the green function, because as I said, we know that the response function lies on the pullback attractor, so a single realization might not be represent enough to get the green function. And then we use the convolution, as in the previous equation 7, to predict the response to a transient forcing of the same amplitude as the step-like forcing that we had applied. And this is what we are trying to do for the first time with an ensemble of carbon model realization with a state-of-the-art model. So we use this MPI Earth system model in a coarse resolution. That means that it has a spectral truncation of T31, and we get two ensembles. One with the step-like forcing, and we let each realization run for 2,000 years in order to sample the slow response of the oceans, that is more or less this order of magnitude, and another ensemble with the 1% CO2 scenario, meaning that we increase the CO2 concentration by 1% every year until doubling, in order to test the prediction that we get from the green function that we compute from the step forcing experiment against the actual simulation that we perform in the 1% CO2 scenario. We focus ourselves on a few observables, the 2 meters temperatures, as I said, because it's the usual proxy of the global warming, and some observables representative of the large-scale overturning circulation in the ocean. So the Atlantic meridional overturning circulation, as computed across the 26 north degree of latitude, and the Antarctic circumpolar current as computed across the Drake Passage. So for the predictor, basically, it is, it can be shown that the Green's function it can be trivially described as basically the time evolution of the observables times the amplitude of the forcing. And as I said, our predictant is the 1% CO2 increase, and we let it run after the CO2 concentration have reached the CO2 doubling compared to pre-industrial conditions for 930 more years. So Let's start looking at the 2 meters temperature. These are the this is the time evolution of the ensemble of instantaneous doubling CO2 in red and of the 1% CO2 scenario in blue. And we see that basically the CO2, the instantaneous doubling lets the 2 meters temperature reach some anomalies of 1.5, say, Kelvin after a few decades, and then a much slower increase goes on that is basically representative of the slow mode of the ocean response. Basically, the two scenarios differ in the first 70 years when the ramp function is ongoing, whereas the two scenarios evolve similarly. I forgot to mention that the simulations have been synchronized and have been set in a way to have the same initial conditions for each realization. Anyway, they after the ramp function ceases, so the CO2 concentration is stable for the 1% CO2 scenario. The two experiments seems to evolve in a similar way. And first sight, we might also say that qualitatively the two simulations, at least the simulation with the instantaneous doubling, looks like a superposition of exponential relaxations. That is more or less what inspired the Hasselmann cold stall problem approach. But we will see that we won't make any assumption about exponential relaxation, nor about the timescales of this relaxation. So if we compute the green function from the instantaneous doubling, the upper right panel shows what it looks like. So at first we have a very strong value, and then we have a slow decay, and the value of the green function becomes more or less 1 to 2 orders of magnitude smaller than the initial value after 70 years, after 100 years. This is suggestive also of pretty much sorry. Yeah, this is suggestive pretty much of a separation of scales among the atmospheric response that is in play for the first years and the much smaller and slower oceanic response for the successive years. So if we convert this Green's function by the time modulation of the 1% CO2 forcing, and we get it in the lower right panel as a blue solid curve, we see that if we superimpose it on the actual simulations, the prediction does pretty much a very good job because it is superimposed on the ensemble mean evolution of the actual simulations. And also we see that after the simulation is stopped after 1,000 years, we can also see that there is still an increase in the near surface temperature for by a few dots of kelvins for at least 1,000 years more. If we focus now on the oceanic variables, the MOC, as I said, is the mass transport across the 26 north degree of latitude in the Atlantic Ocean, and whereas the Antarctic circumpolar current, which is a mixed wind-driven buoyancy-driven current that streams across along the northern edge of the Antarctic ice sheet, is computed across the Drake passage that that is the passage between the Tierra del Fuego in Southern America and the Antarctic Peninsula. This is also the strongest, actually, mass transport that we can get in the global ocean, and this means that it is very important to look at what is the response of these observable in when a CO2 forcing or when a greenhouse gas forcing is applied. So, if we look at the MOC, the time evolution of the abrupt CO2 doubling is shown in the upper panel, and we can clearly see that there is an initial reduction for the first 150 years, and then there is a slow recovery toward a value that is actually never the same as it was before the forcing was applied. The Green's function in the inset reflects this, because at first its value is negative, then it turns positive after 150 years, and it is slightly positive for the rest of the, for at least the 1,000 years that we show here. Again, if we look at the lower panel, the prediction that is shown in the blue solid curve reflects very well the evolution of the 1% CO2 simulation, and it also stabilizes after 1,000 years to a value that is something like 5% smaller than the pre-industrial value. If we then look at the Antarctic circumpolar current, we see that it is pretty much similar in terms of slow response to the evolution of the MOC, but there is an initial increase in the first decades that is probably related to the feedback of the wind forcing, because, as I said, the ACC is a mixed wind buoyancy river circulation. That is not actually very well resolved by the linear response, as we can see in the lower panel. There is actually an initial increase that is predicted by the response theory, but it is much smaller than the actually simulated increase. We think that this is related. Well, this is per se actually a proof that some non-linearity is occurring at these time scales and in this region on these observables, and we think that this is related to the way the surface winds above the Southern Ocean are affected by the CO2, by the greenhouse gas forcing. As a last thing, we also try to look into some regional patterns. So we focus on the sea surface temperatures in the exotropical Northern Atlantic. Why this? Because this region has always been, the evolution of temperatures in this region have always been understood as being affected by a negative feedback related to the response of the freshwater influx from Greenland and from the Arctic ice sheet that was slowing down the Atlantic meridional overturning circulation, as we had seen before. Again, the linear response theory is able to detect these, meaning that as soon as the ramp increase in CO2 concentration is stopped, as we can see in the lower panel, the increase in the SSTs over this region is stopped for almost 1 century, and this is because of the transient response of the meridional overturning circulation to the greenhouse gas forcing.
Sorry, Valerio, you have 2 minutes.
Yeah, I think I will skip this.
Okay.
And I will jump to the conclusions. So we have applied an algorithm to retrieve the first order green function for the response of a generic observable in the climate system. And we have seen that for suitable choices of the forcing, the retrieval of the green function is particularly trivial. And we can use the green function that we get from these suitably chosen forcing to describe the evolution of the system to any other kind of forcing, provided that it is a weak perturbation to the unperturbed state. We demonstrated that the algorithm is pretty much capable of describing the evolution of few key observables in typical forcing scenarios, such as near surface temperatures, the ACC and the AMOC. And basically, we would like summarizing the take-home message of all these is that we can choose the simulations that we actually have to carry on with the state-of-the-art climate models in order to understand the response of the climate system to other kinds of forcing without need to run in simulations with whose boundary conditions are those forcing that we want to analyze. So thank you for the attention. Here are some references, and most of the analysis is included in a recently accepted paper on scientific reports that you can find as an open source paper. Thank you for the attention.
Okay,